Hello, this is Dr. Reed, and this is the Chapter 11 analysis video. In this video, I will go over the end of the chapter exercise number 2, A and B, on pages 344 and 345. So the question that's posed for number 2 is, to what extent does initial test performance relate to performance on a final exam? Here are the data. The exam scores are percentages. So you can see that this is a fairly small data set with 9 students who took a first exam and then took a final exam. And you can see that the most you could score on the exam was 100 and the lowest possible was 0. So here is the data set that we will use to examine this end of chapter exercise. So I loaded that information into Jamovi and went to ESCI and ran a correlation for a single sample because we just have our 9 students who were tested on an initial exam and a final exam. So there's just one group of students there tested twice. And here's the output. So you can see the table here. It's giving you the mean of the first exam and the mean for the final exam. 87.7 for the first exam and about 86 or so for the final exam. There's our confidence intervals for the first exam and the final exam. There's the margin of error for each exam. You can note too on that first exam, the margin of error is fairly large there. And if you look at the confidence interval, you can see that the plausibility values range anywhere from a score of about 77 to 99. And so that's a pretty good size margin of error there, or variability in those plausible values. There's the standard error of the mean for each of the 2 exams. The n is 9 in each group, and for a correlation, the degrees of freedom is n minus 1. And it also gives us the output for the actual correlation statistic. Once we look at a scatter plot for this, we're going to put the first exam as the x horizontal axis on the scatter plot, and the final exam will be the y, or the vertical axis, on the scatter plot. So the effect here that we're looking at is sort of the first to the final exam and its relationship. We get an R of 0.57. So small r is the symbol for a single correlation, which is what we have here. And 0.57 is somewhere in the middle of the range. If you recall, the correlation coefficient ranges from a -1, meaning a perfect negative association between the 2 variables, through a value of 0, which is no relationship between the 2 variables, to a +1, which would be a perfect positive relationship between the 2 variables. And we have about a 0.6 for this. And then there is the confidence interval for the correlation coefficient. And that ranges from a -0.18 up to a +0.89 for our upper limit. So make a note of this confidence interval here. We're going to come back to that in a slide coming up. And you can see that it appears that 0 is in that interval. So it appears to be a plausible value. And we supposedly at this point cannot really rule that out. However, you should make a careful note that our sample size here is what I would consider to be pretty small, and that's only 9 people. Okay, so you have to think about the width of that confidence interval relative to that fairly small sample. The output also gives you, if you look over here to the right, a picture of the confidence interval for this correlation. And so the null, if you were running a hypothesis test, you might set the null as a population value of 0. Note here that this is the symbol, the Greek symbol rho, for the population parameter for the statistic R. And there's our confidence interval. So this is a picture of what was on this table down below here. And there's the correlation, is the blue dot going over to about 0.57. And as you can see, just like in the confidence interval, it looks like the 0 is within that interval. I wouldn't call it being comfortably in the interval, still is in the interval. So make a note of that. And the other thing you want to note here is if you look at where the blue dot is, the actual correlation value within its confidence interval, note here that it's not in the center of the interval. And this is common of the correlation because the correlation, the sampling distribution for the correlation is usually, not always, but usually not symmetric or symmetrical. And that is because by definition, the correlation is bounded by a -1 up to a +1. And so if the population correlation, for example, is say zero 0.6 or zero 0.7, the sampling distribution tends to be skewed down towards the negative side if you have a fairly high population correlation. And that's because in terms of the sampling, there's not as much room from where that population parameter might be to the upper limit of the values that the correlation can take. And there's more room down below. And so it tends to be asymmetrical because of the bounding of the statistic between a -1 to a 1. So as you see here, just like I explained, we have supposedly a population that we're estimating of about 0.6, 0.57 to be exact. And so the interval here tends to not be symmetrical because its sampling distribution is going to allow more samples down here because we can go all the way to a -1. And up here, we can only go up so far, the highest being a +1. So there's less room up above where our point estimate is. And so we tend to have it bunched up here. So just make a note of that. There's nothing wrong with the computer there. The typical scenario is that it's a little bit asymmetrical as opposed to the confidence intervals that we've been looking at in terms of the means, which usually are symmetrical. So let's take a look at the scatter plot now for this output. And we will look at the database one more time. So here are the data, and same as before. And what I did with this slide is take the first exam. If you look on this column here on the right, I took the score for the first exam for each person and then subtracted the final exam from it to get these values over here on this right column here. So you can see the difference between the first and final for the first person is a -13. So on the first exam, they got an 85, and on the final, they had a 72. So they went down 13 points. The next person went down 4. Next person went down 4, etc. And there's 3 individuals who went up. This person went up 6.7, went up by 5 from the first to the final. This person went down 19.8, almost 20 points, etc. This person went up 21 points. So the reason I'm doing this is because I'm going to break apart this scatter plot for you just as an instructional way of kind of reviewing what the scatter plot looks like and a way to kind of get an idea of what's happening with your data. So let's take a look at the scatter plot. So that's the scatter plot over here on the right that I just pulled up. So we have the first exam down here on the horizontal axis ranging from 0 to 100. And then on the y-axis would be the final exam, that also ranging from 0 to 100. And then I have the points plotted over here. So before I go to the points, you see this dotted line in the center here. This is called the line of identity. This is called the line of identity. Now, I did this artificially. I just put that in there myself to sort of help us see how the scatter plot can give us information about the data that we have. And the line of identity is a line whereby the x value is equal to the y value. So if you look here, it would be something like this. If x is 10 and y is 10, we'd have a point right there. When x is 20 and y is 20, there's a point right there. So it just goes up diagonally all the way to the top. The reason I put that on there is because it can help us kind of see what's going on with the data. So let's go back there and look now. I've color-coded the data points to match what's going on over here in this right-hand column. And as you can see, what's interesting about having that line of identity is you can see that there are 3 green values here where people increased from the first exam to the final. And there's also 3 then green points that match those. They're above the line of identity, meaning whatever the score was for the first exam, the final was higher than that score. Hence, those values are above the line of identity. And likewise, for the other ones that are in red, this is a case where compared to the first exam, the final exam is lower than the first exam. So we would expect those values to be below the line of identity, as you see here. So this is just a way to kind of look at it. So if you focus your attention on that last person down here, number 9, take a look here at this value right there, the 21 increase, right? We went from 54 to 75. So what you should be able to do is you should be able to come over here to this scatter plot and pick out which of the 3 points is represented by this person here and the increase. So take a guess. I'm gonna plot that out for you, and I'm gonna match it up with the little green dot there. And so that point is right there. That's the point. And if you break this apart, you can see why that's the case. So if you look at the raw data, I went from 54 to 75. So I go 54 on the x-axis and then go up to 75 over on the y. And that's what matches for my point. And that's the same for all the points in the scatter plot. And then if you take a horizontal line from the line of identity here and look at the difference between these two, we get our increase of 21 points, which is being shown here. So essentially what you see on the graph here, or the scatter plot, is just a picture of this last person's information, including their 21-point increase from the first to final exam. So the other thing you can do is get some descriptive statistics for the data that you have, and I've done that here. And if you look at the standard deviation, so you can get a sense of the variability between the 2 exams. So the standard deviation for the first exam was 14.35, and the standard deviation for the final exam is about 9. So you can see that there's a little bit of a difference there. There's more variability on the first exam than there is on the final exam. And so if I shade out the data points over here with this blue square, we can see that it's sort of it's not a square, it's actually a rectangular shape. And what that's doing is depicting the fact that there's more variability here going this way, represented on the x-axis with this value here, than there is vertically this way on the y, which corresponds to this value right here. So the reason I'm doing this is just to get you into the habit of kind of looking at the information you have to see if things kind of match up and how you can kind of break things down so you understand what's going on. So that's another way of making the graph represent pictorially what you have in terms of the numbers for your data. So the actual exercise, letter A, says that we should generate a scatter plot, which we did, as you see over here on the right hand side. And you will hear this several times in this video. Always do scatter plots for correlations. And that's going to become evident on the next slide. First thing we can do though is if you look at the scatter plot, can you eyeball a correlational value? Well, we know what it is from that previous output from ESCI, and that was our 0.57 positive. So we know that this is a positive correlation because as there's a tendency for the X to go up, there's a tendency for the Y to go up. And so we have this sort of from the lower left going to the upper right, we have a little bit of a pattern there. Now, the other thing you can do with correlation is do what's called the coefficient of determination, and that's simply the R value squared. And what that is going to do is give us a representation of how much variability in one variable can be accounted for by variability in the other variable. It works both ways. So whatever value you calculate for this, so for example, if I squared 0.57, I'm going to get 0.33. And if I multiply that times 100, I get 33%. So what that essentially means here is that 33% of the variability in the final exam, which graphically is sort of the dependent variable because it's on the y-axis, 33% of the variability in the final exam scores can be explained or is accounted for by variability on the first exam. So the final thing on this slide that you can kind of look at is if you look at the data points here, and there's not very many of them, and that's a problem we're going to talk about in a second. If you look at the data points here, there's one of them that seems to be a little bit kind of out of the main cluster of points. And that would be this point right there. And so if let's just say that this might be called what you call an outlier. We don't know if that is or not. We're just kind of looking at it to show you what might happen. So what I did was I reran the analysis with this value removed as if it were an outlier. Again, we don't know if that is one or not, but let's just say it was, and you can potentially guess what would happen to the correlation if this value was removed. Well, with this value in there, you see this kind of a shape, kind of an elliptical, kind of an oval shape here, giving us our 0.57. But if you take this value out, we end up with this more, maybe a little bit more of just a bunch here that's more circular. And in that case, when you do that, by removing this value here as a potential outlier, the correlation is going to go down by quite a bit. It drops from 0.57, and with this value gone, it goes down to about 0.41. And so, and the R squared goes from 0.33 to 0.17. So the R squared is kind of cut in half. The point I'm making here is um, we have a case where we don't have very many points. And so that's a problem. And by removing just one point, if it's an outlier, that can really change your results dramatically. So you want to kind of keep that in mind when you're, looking at data. And you'd never want to remove a point unless you knew for sure it was an outlier. And there are ways to statistically test for that. Letter B then is going to ask us if there are any cautions or concerns, okay, for the use of R to describe this data. And I've mentioned a couple already. And so, yes, there are. And let's take a look at some of those potential issues using our scatter plot. So the first issue you can look at is, again, that potential outlier situation. And so what I'm doing now on this particular slide is I'm presenting some issues. There's about 8 or 9 of them. And each one of them I'm going to represent using the same number of data points, but in the new scenario. And we need to ask ourselves whether that's what we have or what we could have with our data. And so, to repeat, this first point here would be the potential outlier, but we're really not necessarily sure whether that's going to be an outlier or not because we just don't have enough data to say whether that's the case. A second issue then is the pattern, is it linear? Is it linear? Well, if I took the same number of points or roughly the same number of points, which there are 3, 6, 9, 3, 6, 9, and sort of stretch them out in a nice pattern like this is what the data might look like if it was highly linear in nature. We can put a line of best fit right through there that almost fits the data perfectly in a positive direction. Now, whether or not the data that we have could be linear or not, we're not sure, but my guess is that if you had more data points, it probably would come close to that. So our conclusion there is that given the situation, our data is probably linear, even though it doesn't look like that right now. It's because we don't have enough data points to determine that. The next issue then is whether it would be nonlinear, and what would that look like? Well, here's a scatter plot showing 9 or so data points if they were non-linear in nature. So you can see that they kind of curve around here that I'm showing with my pointer, making sort of some kind of a curve that can be represented by a curved line. This is clearly a pattern that is not linear. Now, with the grouping of data points that we have for this example, my guess would be that even if we collected more data, we would probably not end up with a nonlinear situation. So you might conclude there that that's not a likely scenario for what could be our potential if we had more data. There's a couple of them here now that I'm going to present the book doesn't talk about, and one of them is called the orange kumquat effect. The orange kumquat effect. What would that look like? Well, it would look like the following. We have a situation where you have a set of data that's sort of clustered maybe on one end, and then there are maybe 1 or 2 points way away from that that would be considered outliers, right? And there would be way down here. Now, this is where it's important that I'm going to say it the second time now, is why you want to make sure that you do scatter plots with your correlations so you can see what's happening. And the issue here is that if you don't look at a scatter plot, the computer can fit a line between these two groupings of points and give you a fairly high correlation. The computer in this case might give you a correlation around zero point 0.6 or zero point 0.7 or even higher. And so you might think, oh, that's very good. But when you look at the actual scatter plot, you can see that that's not good because there's no data here in the center. And so you really can't do anything. The second issue is these would be considered outliers. And if you remove those two data points, your correlation is going to shrink down considerably because now you basically have no relationship when you just look up here at this cluster. This is called the orange kumquat issue. A great example of why you want to make sure you look at scatter plots when you look at correlations. And would our data have that? I would guess probably not, but we can't be totally sure. So my conclusion there is, we can't really tell because we only have 9 points. I'm guessing it probably wouldn't be this because we have a test here, right? And it ranged from 0 to 100. And so it's pretty likely that there's at least a few students whose scores would be in this middle range here. The next one is called the dumbbell phenomenon, and that's similar to the orange kumquat. And it's a case where you basically have sort of two clusters here of data that can be joined by a linear line. And once again, you have a case where you can't make any conclusions about this because there's no data in the center. So what you basically have is no relationship here and no relationship here. But the computer sees this as like two big data points. And so your correlation is going to be much larger than what it really is. Would be not acceptable. You couldn't draw any conclusions from this, other than the fact that you're missing a lot of data in the center. Would we have this? You can't really tell. I doubt it, again, because it's a test, so there's probably people who scored in the center. And so I'm going to go with can't tell on the dumbbell phenomenon. And then there's range restriction. Now the book talks about that, so let's take a look at that. Now what I've done here is this is the actual original data, and the test range was 0 to 100. And so you can see that our range only goes from about 100 down to about 50. So if I go up here, I have 50, and I range up here to about 100 on the x-axis, and then on the y-axis, I'm ranging from about an 80 to 100. And so what would it look like in order for us to not have range restriction? Because that's really what we have here. It would have a circular, our pattern would fill in this from the range that we can get. Okay, so this is a case where there's a problem with the test somehow, in a sense that everybody's scoring up here and nobody's scoring down here. It's potentially a case where the test is just simply maybe just a little bit too easy for everybody. And so the conclusion here is that yes, one of the main issues with this data is there's range restriction. And we know that's the case because we know that the test, both of them, ranged from 0 to 100. That's a fact. So that's already known. And our data that sits up there does not fill in that range at all. And so we have a sort of a diagnosis of range restriction. And what that does is it will artificially lower the potential value of your correlation. Okay, so we had a 0.57. If we didn't have range restriction, it might be much higher than that, up around maybe 0.8 or so, which is a fairly big difference. And then there's two more to go. There's this what's called a ceiling effect and a floor effect, so I'll show you both of those. Here's an example of what would be considered maybe the ceiling effect. And on that, you have a case where the data points tend to be kind of clustered up here around the top. There's a few people that kind of tested here, started out on the first exam with maybe like a 40, and then they stayed about the same for the final. And then this person started out at about a 58 and went to about a 78. Okay, and so a few people kind of improved, but a lot of people just kind of clustered themselves up around this high level on the final exam, regardless of whether they scored an 80 or a fairly high score on the first exam. Most of these people are kind of bunched up here at the top on the final exam. And so this would be a case of what's called a ceiling effect, and is indicative again of maybe a test that would be a little too easy, in a sense that the people who scored high on the first exam are not really getting a chance to score even higher than they could based on their knowledge, because they can't go any higher on the final. And so you end up with this pattern where you've got a clustering of values up here, and that's considered a ceiling effect. Ceiling effect, and that can affect your the value of your correlation. Typically make it just a little bit lower than what it should be. And so we potentially have something like that, but we can't, again, we can't really tell because we only have like 9 data points. And the last one is the floor effect. And that one, like you might guess, is the sort of the opposite of the ceiling effect. We have people who, for example, scored fairly low on the first exam, but then they improved quite a bit for the final, if you look over here. And then here's a person who scored 27 on the first exam, got about a 35 on the second one. Um, but then you have all these people down here who scored fairly low on the first exam, but they, if you look at where they are, they also didn't really improve much on the final, and so they sort of couldn't improve very much from the first to the final exam, and they're not able to sort of get out of the bottom of the test. And so this could be a case where the test is maybe a little bit too difficult for people. You've got too many people clustered down below here at the bottom part of the scatter plot. Whether or not our data would look like this, I doubt that's the case. And the reason why is because our original data is more clustered over here at in the upper right-hand corner of the scatter plot. But that's an example of the floor effect. And so we can't really tell, but I would probably say that maybe wouldn't be the case. If anything, it looks like the exam might be a little, particularly the final, um, might be a little too easy, or even both tests were fairly easy. So the main point of this slide, though, I want to present that now. The main point of this slide is that there is not enough data to determine with confidence the true scatter plot pattern depicting the relationship between the first and the final exam. So that's what you want to keep in mind with what we're looking at. We have 9 students, and that's just not enough for us to spread those data points out across the scatter plot to get the range of values in the exam that we administered, or both exams, to sort of have a realistic indication of what's going on there. And so you're having to go back to the drawing board on this one. Trying to determine what's going on with only 9 or 10 data points is pretty difficult. Then the last thing I'm gonna present for this thing is, and I've talked about this, I believe, last semester just briefly, but it has to do with making inferences regarding your effect sizes, which would include mean differences like d-values and also correlations. And what we'll talk about here is called the counter null effect size. And in this case, it looks like it may come to the rescue with our original result. So let's define that, and then I'll give you a couple of examples. So the null counter null interval is an interval with the null, typically 0, as the lower limit, and a non-null effect size, which would include a correlation, as the upper limit. That will end up being supported by the same amount of statistical evidence as the null. the null counter null interval is useful because it provides a conceptual hedge against two common interpretation errors. And I'm going to take a look at both of those right now. The first one is the following. Number one, assuming an effect size is 0 or not important when the p-value or the confidence interval, sort of in a way, fails to provide evidence to doubt the validity of the null. This often happens with small samples. Small samples have greater sampling variability and low statistical power, such that mean differences or relationships, i.e. correlations, that may have practical importance often produce p-values that fail to provide probability evidence to doubt the validity of the null. And that's first thing is you can see that I put here the correlation is an effect size commonly used in meta-analysis. And this first interpretation error, if you think back to our confidence interval that we have for our example, we have the R 95% confidence interval of a minus 0.18 to 0.89, which is a fairly wide interval. But remember, we only had 9 people. And so this is what we're talking about. We have a small sample where we are including 0 in that interval. And I'm going to show you an example on the next page where the counter null value can kind of help us from thinking that what we have here is basically no correlation because 0 is in the interval. Okay, so kind of keep that in mind. And let me give you the second interpretation error, which sort of like a mirror image of this first one. The second one is assuming an effect size is important in magnitude when the p-value for the statistic provides evidence to doubt the validity of the null, i.e. 0 is not in the interval. This often happens with very large samples. Very large samples have little sampling error and abundant statistical power, such that even tiny mean differences or relationships that may have little practical importance often produce p-values that provide probability evidence to doubt the validity of the null, i.e. 0 is not in the interval. And so you get this false potential impression that you have something there because 0 is not in the interval when you sort of really don't, okay? And the counter null can kind of help you reorient yourself so that you don't misinterpret the result that you have. So a good way to think about the null counter null interval is that if the counter null value, which is typically the upper limit, the lower limit is typically the null, which is usually 0. If the counter null value were taken as the null value, the p-value for the statistic would be the same as the p-value obtained when the statistic was examined with respect to the null. Now I know that's a mouthful. Well, not only a mouthful, it's just a hard one to maybe wrap your head around a little bit. What I'm going to do is I'm going to provide you with an example that deals with that first interpretation error, number 1, that I read through up here. So let's take a look at an example because that'll kind of help you to see how the counter null effect size in this particular example that we have here with these 2 tests, the initial exam and the final exam, and our R of 0.57 and our confidence interval for the R of minus 0.18 to 0.89. How the counter null interval may kind of help you reorient yourself in terms of maybe what you have as potential here for your result. So let's take a look at an example here. The numbers are different than what we have for the testing example from the book, but the concept is exactly the same. So I have a schematic for a population, or equivalently the random sampling distribution of R from a population with rho equals 0. And you see that right there in the picture. So here's the example. This is a study that you did, for example. You select n equals 30 and you calculate a correlation or an R observed. I'm calling that R calculation there. You find an R calculation of 0.20 with a p-value equal to 0.15 and a 95% confidence interval equal that ranges from a minus 0.17 to 0.52. And you conclude that the p-value fails to provide probability evidence against a null R population of 0. Okay, and the reason why is because remember 0 is in that interval. 0 is a plausible value here. So you can't rule out the notion that this R calc is essentially 0. We can't rule out the notion that R is potentially 0 because it's in that plausible interval here. Okay, so you want to be able to hedge against that using this counter null. Okay, so you conclude that P failed to provide probability evidence against a null R pop of 0, implying that 0 should not be ruled out as a plausible value. But the sample is relatively small. So R calc may have overestimated R pop by 0.2 because of sampling error. That is, the difference between R calc and R pop could simply be due to sampling error. Okay? Okay. And so if you're left with just this, your conclusion is that, well, I can't rule out 0, and so 0 is a plausible value. So I don't have a lot of evidence against the null here of 0 with my observed calculation of 0.2. Maybe, maybe not. Let's take a look. There it is there. There's where you sit right now. Okay, you found a R of 0.2. There's your null for your sampling distribution or your null correlation of 0. However, there is another possibility here. Another possibility is that R pop is not 0. Because remember, we don't know what R pop is, typically, as from the first semester. It's not 0, but greater than 0. Maybe the population, the actual population correlation is not 0 after all. And maybe it's more above 0 than R calc is, such that R calc, instead of overestimating a null of 0, actually underestimated R pop. By this logic, a R calc value above 0 provides just as much evidence that R population is actually 2 times R calc as it does R pop equals 0, because the difference between R calc and 0 is the same as the difference between R calc and 2 times R calc. In this sense, the results provide just as much evidence that 0.4 is a plausible value as the notion that 0 is a plausible value. And there's where that counter null value comes into play. So if I move it over here, if you look up above, what happens if the actual population correlation is here instead of here? So the null counter null interval is 0 to 0.4. Your results are as consistent with the notion that 0.4 is plausible as with the notion that 0 is plausible. If the null had been 0.4 instead of 0, the p-value of 0.15 down here for R calc would have been the same. So if you notice here, the null counter null interval is 0 to 0.4. It's basically double the R observed value. And here's your confidence interval here. So you can see that the null counter null interval fits inside the observed confidence interval here. So the point of the matter is that you shouldn't always necessarily focus on the negative, if you will, okay? Because it's possible that the population correlation isn't 0, but it's actually 0.4. And if your if your observed correlation is sort of different from 0 just due to sampling error, well, then the sampling error can occur on both sides. Maybe the sampling error caused your correlation to be above a 0 pop, or the sampling error maybe in fact caused your correlation to be below a 0.4 population, because sampling error is like random error that occurs on both sides of the population parameter. Okay, so this is the notion of the counter null coming to the rescue. What do I mean by this? I mean that during a dissertation, or if you try to write up a paper and someone is arguing that 0 cannot be ruled out, you can argue with just as much logic that 0.4 cannot be ruled out with the exact same notion. And so sort of think positive basically in order to get that one. Okay, so that's what's called the null counter null interval. And it works for correlations and d values. So that's an extra that I'm throwing in there that the book does not do. A little hard to wrap your head around it, but it could come to the rescue if someone is telling you that your correlation here of 0.2 means there's no correlation. It could in fact mean that in fact there is a correlation. It's just higher than what you found, not lower than what you found. Okay. Let's summarize. Always do scatter plots when analyzing correlations. Always do scatter plots when analyzing correlations. The R 95% confidence interval is usually not symmetrical, but it can be if the population correlation is 0, right? Because then we can balance out the samples on either side to get a potentially symmetrical interval there. The line of identity, x equals y, can be helpful when examining scatter plots. R squared times 100, which is the coefficient of determination, measures the percent of variance in a dependent variable that can be explained or can be accounted for by an independent variable. So make a note of that. That'll come up again when we do the chapter on regression. The correlation R can be misleading if it's taken at face value. That's why I did the slide where I looked at all those different scenarios to see what you always want to see what the picture looks like, not just the value of the correlation. And finally, you want to consider the counter null interval, particularly if a 0 null is in the 95% confidence interval and it's fairly close to the lower limit. And that would be the case for the example of the initial test, final test correlation, and also the example that I just gave you in the last couple of slides. And the last one is always do scatter plots when analyzing correlations. This is not an error. I'm repeating this on purpose. Okay, well, thanks for watching. There'll be a 5-point quiz on that. And as always, if you have any questions about anything, please send me an email.